session 9 of ITCS, the proof complexity session. And I have it bracketed like this because we have proof complexity in sort of two different senses of the word, so I'll say a little bit more of that later. So the topics, the themes in this session are both proof complexity and also the complexity of finding an error in a proof. Okay? So the first paper is Size, Cost, and Capacity, a semantic technique for hard random QBFs by Olaf Beiersdorf, Joshua Blinkhorn, and Luke Hind. The second paper is called Stabbing Planes by Noah Fleming, Robert Robert, Paul Beam, Russell Impagliazzo, Antonina Kolokolova, Dennis Pankratov, and Tony Patasi. And the final paper is Towards a Unified Complexity Theory of Total Functions by Paul Goldberg and Christos Papadimitriou. So the first paper is about refuting quantified Boolean formulas, or QBFs. So you might remember QBFs from a long time ago, or you might work with them every day, but for those of you who need a reminder, quantified Boolean formula is just a Boolean formula where I'm allowed to put as many quantifiers as I want beforehand. Right? This is a complete problem for p-space, maybe the canonical complete problem for p-space. And it's common to think of it as a two-player game where the exists and for all players take turn assigning variables. And the there exists player wins if there is an assignment that satisfies the Boolean formula, and for all player wins if there's not one. So in this paper, the big innovation is that the authors give a new technique for proving lower bounds on the size of refutations in proof systems that have for all reduction added to them. And this technique is called size, cost, capacity theorems. So basically, the canonical thing to do to lower bound, or to show that the for all player has a winning strategy, so to show that a refutation exists, is you, like to prove a soundness for these proof systems, is you look at the refutation that the proof system produces, and you show that you can extract a strategy for the for all player to show that it wins, right? So this proves soundness for the proof system. And here what the authors do is, I'm not going to say anything very precise, I'll leave that to the next speaker, but basically what they do is they make the extraction of the strategy quantitative in some way, and this gives them a lower bound on the size of the refutation, right? So they're able to show that if you want to refute a QBF, you have to use a refutation of size at least something in your specific proof system. And then they use this technique to prove several new lower bounds, including a new lower bound, the first one for a certain family of hard randomly generated quantified Boolean formulas. And they also reprove some known lower bounds in a cleaner way. The second paper is called Stabbing Planes. Okay, and so think back to SAT solvers and the DPLL algorithm. This is probably the algorithm that modern SAT solvers are based on, and it's based on the following thing. What you do is you have some SAT formula, and at every step you assign a single variable to either 0 or 1, right? So you branch on the value of this variable, and if you reach a contradiction, you back up and you unwind the recursion, and then you continue. So here's a visual representation of what's going on. Here, what the authors do is they generalize this to the following proof system called the stabbing planes proof system. So they introduce this proof system for the first time, and instead of branching on single variable assignments, they're going to branch on linear inequalities, right? So integer valued linear inequalities. So instead of having xi equals 1 at every branching point, they're going to have an inequality like ax greater than or equal to b, or ax less than or equal to b minus 1. Right? And because you're working with integer valued x, this kind of formula is exactly what you would have. Okay, so they introduce the system, and then they actually show that it's equivalent to Krajicek's tree-like refutation plus cutting planes. But because their formulation is so simple and clean, what they're able to do is they're able to prove a bunch of new equivalence results that weren't known before, or relations that weren't known before. So they're able to show that stabbing planes is at least as powerful as the cutting planes proof system, which is a very widely studied proof system, in that you can simulate cutting planes proofs of various kinds with a comparable size and rank of the proof. And they also show that stabbing planes may be actually stronger than the cutting planes proof system because they're able to show that there are quasi-polynomial size refutations for Titan formulas, which are formulas that are believed hard for cutting planes. Okay. So, and then they leave open an intriguing direction, which is, would this technique be helpful for stat solvers, right? So currently stat solvers branch on the value of single variables. Can it be helpful to actually branch on linear inequalities, right? So here they don't make concrete progress, but they leave it as an interesting open question for future work. Okay, so finally, towards a unified complexity theory of total functions, this paper isn't about proof complexity per se, but let me explain why it still fits in with the theme. Okay, so TFNP is a complexity class, stands for total functions in NP. And this is the complexity class of functions for which every input must have at least one output, and you can verify that that output is a valid output efficiently, but you can't necessarily find it. So you should think of problems like factoring, okay, and Nash equilibrium. So factoring, right, if I have a factorization of a number, I can easily verify that it's equal to the number, and also there always must exist a factorization of the number, but it's not necessarily efficient to find it. And for TFNP, we don't know any complete problems. And also, in some sense, it's unlikely that there will be any complete problems for TFNP. There's some evidence that points to that. But there are several famous subclasses of TFNP, like PPP, which contains PPAD and PPADs, and PPA and PLS. These are all problems, complexity classes which are defined by complete problems like pigeonhole principle, or every DAG has a sink. And these famous subclasses all do have complete problems. So the authors set out to ask, is there a class that contains all of these classes that also has a complete problem, so that we can start to shed some light on the complexity of these classes of total functions. Okay, and they define a new class called provable TFNP, which has the following complete problem. The complete problem is the wrong proof problem. So, I mean, the setup for this is a little bit technical, so I'm not going to say exactly what it is, but essentially, you're given a wrong proof for a statement, right, where you derive false. And what you want to do is you want to find one incorrect line in this proof, because if the whole proof is incorrect, there must be at least one incorrect line. So that's the complete problem for this class, and it actually turns out that it contains all of these different classes. Yeah, so that's it, and please enjoy the session, and we'll welcome the first speaker, which I believe is Josh.